Welcome everyone. Let's do this, huh? Take a look at angles of insulation. And by now, that should mean a little bit of something to you. If you don't have this activity, it's available on my site or in the classroom. A couple of things that you could have that are helpful but not necessary. A protractor. I can show you a workaround if you don't have one, or maybe you've got someone in your household who's kind of handy with tools. They've got a speed square. That'd work pretty darn good as well. If not, like I said, we can kind of guesstimate some of these angles that we're going to refer to as a low, medium, and high. If you have graph paper, that's helpful, but again, it's not really necessary. It just is an easier way of adding up some area, but we're going to actually make a calculation that will not require the graph paper, but keep it looking sophisticated and high tech. A calculator is helpful. If you don't have one of those, I bet you've got one on your old cell phone, and the same holds true for flashlights. If you don't have a flashlight, like this guy here, you probably can just use the flashlight feature on your cell phone. So we are, again, at a spot where we've talked about angles and how they're useful for describing things in the night sky. And here we're going to look at angles of insolation. That's basically a fancy way of saying energy from the sun. How is that energy from the sun affected by different angles? And we're basically going to look at 3 angle types. And without getting into the numbers here, we're just going to say, all right, if this is you, well, actually there's Earth, and then there's you, and you've got 3 different angles. I would call this a relatively low angle, which we don't have to, but if we wanted to put our old protractor on there, we could measure that guy out. I would call something like this like your medium angle, and as you start to get close to directly overhead, 90-degree angle, that would be a high angle. So 90 degrees would put the sun at your zenith. You should also be at a spot and say, Cash, if that's me, I must be on vacation, because we know that here in Dearborn Heights, we're at about 42 degrees north. That's above the Tropic of Cancer, or it's above that if this is the Earth. And there's the equator of 0 degrees latitude. And if this is the poles at 90 degree, ballparky, right? We'll say that if this is 42 degrees north, the highest the sun will ever get directly overhead as far as latitude's concerned is this line of latitude here, 23.5 degrees north. And then the lowest in the northern hemisphere we'll experience our sun angles is when the sun is directly overhead the Tropic of Capricorn, or 23.5 degrees south. And then the sun just basically goes back and forth directly overhead there. So do we get a high sun angle in summertime? Sure, absolutely, but it just wouldn't be directly overhead. So keep all that good stuff in mind. Allow me to read this to you. If you want to speed through because you can read on your own, you won't hurt my feelings. I'll just kind of move through with my finger here, and then you can jump to that spot of the video. Background. By now you should be familiar with the 23.5 degree tilt that the Earth's axis is on. And yoink, there's the old Earth. We're tilted, knocked over, probably from a collision from the moon. And we know that, old Polaris is up there. So we've got the 23.5 degree tilt, and that's responsible for us having seasons. The tilt causes 2 changes as we revolve around the sun: the length of day and the sun angle. So I've been saying that the reasons for seasons is rays and days. And while the hours of daylight is varied throughout the year, the major factor for the seasons is a change in angle of insolation. That's the sun's rays angles. So we're going to look closer at these angles of insolation and why. And it has been discussed, right? How do I know, without even running any of this testing, that the sun angles must be important, more important than the length of day? Well, think about it. If you've got places like above 66.5 degrees, north or south above the Arctic Circle, you get near the poles, there's chunks of the year where you experience 24 hours of daylight and also 24 hours of darkness. But think about that. If the sun was out for 24 hours a day, cooking the Earth's surface, it should be blazing hot, but lo and behold, it is not. It's still cold up there. Why? Well, yes, the sun is still out, but the sun angle is very, very low. So yes, the reasons for seasons is the rays and days, which would mean that the daylight hours are longer, still about a 24-hour rotation period, but the rays change, and that's going to be the bigger factor. So here's what we're going to do. We're going to use our little bit of graph paper here. And in this first procedure, it says in the high sun angle area of your graph paper, using a protractor, hold your flashlight at a 90-degree angle to the paper. Make sure the flashlight is directly touching the protractor. Have someone carefully trace the brightest area of light. So here's my graph paper. Ba-boom. Here's my protractor. Ba-boom. Here's my sunshine. How fancy this guy is. See, I mean, I could go like that, but that'd mess things all up. So I'm going to put my flashlight on its brightest area. So this would be like a low sun angle. Here's the sun at the zenith. And I'm going to see if I can get away with doing this myself. So I've got, I know you can't really see it from right there. You're sort of looking at the butte of my flashlight, but just trust me here. I'm going to circle the brightest part of my flashlight. So this is what I'm calling a 90-degree sun angle. So what's that mean? The energy that this flashlight makes at 90 degrees, so I'm off a little bit here, but that's pretty darn close. And you can see I've got that trace there. That's the area that it's cooking or heating up on this paper. So think of that as like sunshine. If the sun is directly overhead, however much energy this represents from the flashlight, it's cooking this smaller area. So let's continue on. Check. In the mid-sun angle area of your graph paper, place the lens edge on the spot provided. Lift the back of the handle 10 centimeters above the table. Measure and record the angle with the protractor. Have someone carefully trace the brightest area of light. So you're going to just have to kind of trust me here that I've done this before so I can show it to you at once. If I lift this guy up and I take my flashlight here and I'm going to lift it at an angle, just kind of trust me here that if I lift the butte of my flashlight up to about a 45-degree angle and then I trace the light, all right, so there is what I'm going to call my 45 or my mid angle. So what the heck are we looking at here? Well, from this about 90 down to this about 45, you can see that the same amount of energy is now being spread over a larger area. So let's continue on and see what the heck do you think? Take a guess right now from what we've seen. The angle got lower and we started to warm a larger area. What do you suppose would happen in our low sun angle? Do you think it's going to cover a bigger area or a smaller area? Let's discover. So in the low sun angle area of your graph paper, place the lens edge on the spot provided. That's going to be against our protractor here. Lift the back of the handle only 5 centimeters above the table and measure the recorded angle with the protractor. All right, so I'm going to hold this guy up here again, and that was about my 10 centimeters of light. And now I'm cutting that in half. I want to try to get this over to, I'm not splitting that. Okay, I'm holding my protractor like a so. And then I'm going to drop that out of the way so I can circle my low light, which was about half of that again. So it's right about 20 degrees on my protractor. But what you can kind of see here is, woo, party time. What you can kind of see here is, as the angle got lower, it's covering a larger area. So think of that again as kind of like this. You're an observer. This is your high angle. This would be like your mid angle, and this would be like your low angle. And this little circle here is supposed to represent the sun. So when are you having the most amount of energy cooked down on you in the smallest area? Does any of this matter? Well, of course it does. It plays a huge role in how things heat up. So let's kind of look at some of these discussion questions here. We're going to try to calculate some area for an ellipse. And an ellipse is just a squished circle. So we're going to calculate the area of all three of these. And this is how we go about doing that. I've got to get my metric ruler. And we've got our low, mid, and high. We're going to have to measure the length of A and the length of B. So let's take a peek at what we've got. In my low area, that's going to be this longest one here, works out to be about 9 centimeters. I only need half of that according to this equation. So half of that would be 4.5 times this little radius here, which appears to be, we'll call it 1.5, kind of rounding a little bit here, times pi. I'm going to do all my calculations at once. So the mid one, I got to get A and B. So in my mid one, it looks like I'm about 5 centimeters. So half of that would be 2.5 times, I'm going to call that 1.75. 1.75 times 3.14 pi. And then my high one, that's going to be this smallest circle, the directly overhead, 2.5. So that would be 1.25 times, I'm going to call that 1.25. Man, almost a perfect circle there. That one's more circular than ellipse. Perhaps we should use a different formula. It's probably squished a little bit. I'm not that crafty. It's actually really tricky to make a perfect circle. Okay, so what do we do here? Little razzmatazz with this bad boy, and we'll get some mathematics out of the way. If I go 4.5 times 1.5 times 3.14, I got an area here of 21 point, I'm going to round that to my hundredths and call it 0.1. Actually, I guess I should probably round this and call it 21.2. And this was centimeters. So this is my cubic centimeters. Excuse me, centimeters squared. Let's go on. At 2.5 times 1.75 times pi. Got that there. I'll call that 13.74. 13.74 centimeters squared. Last guy, 1.25 times 1.25 times 3.14 equals, call that 4.91. 4.91 centimeters squared. Okay, so what the heck does all this mean? Well, basically it just means that for our high angle, this little guy, there's not nearly as much area as our low angle. So it's kind of like an inverse relationship there, right? The lower angle's got a larger area. And then as you would probably have guessed, right, the middle falls somewhere in the middle. But if that's almost 5 and that's around 20, you know what I mean? That same amount of flashlight was being asked to cook or warm or heat really like 4 times as much area. And our low angle was around like 20 degrees and our high angle is about 90 degrees. So that's a pretty big difference, right? Let's take a look at some of these questions because we're probably going to have to come back to that idea. And being that I typed them, we will. So, was the flashlight's energy output the same for all 3 light angles? In other words, did you see me do something crazy with this flashlight or like rig it up to a, super powered battery? No, of course not, right? So was the flashlight's energy output the same? Yes. If somebody said explain, use your own words here, but I mean, I'd say something like, yes, it was the same flashlight, same battery, same power, something to that effect. So yes, all was the same. And you can word that however you'd like. So what relationship between area and light angle can you conclude from this activity? Well, I'm going to just use kind of like some fancy little abbreviations here. And I'm going to say, when we had a large area, so when we had a large area, it was from a low angle, right? This was our lowest angle and it covered the most area. So they're kind of opposite there. Or I guess another way you could say that was, yeah, but when we had a low area, remember that was when the sun was at our zenith or 90 degrees, or our high angle. Basically, you get kind of this opposite. So what relationship between energy and light angle can you conclude from this activity? Well, I would say if you've got a low angle, it's going to equal more energy. And that's per area. So, I mean, again, it was the same flashlight or it's the same sun, whether it's at a low angle or a high angle. But what I wanted you to get here is when the sun's at a lower angle, oh boy, what's the relationship? So when we've got a low angle, did we actually get more energy? No, look at that. The old man made a boo-boo. What's my arrow doing up like that? When we had our low angle, we actually have lower energy. So think about this as kind of like climate or temperature, right? If you had to pack for vacation and I said you're going to lower angle or higher angle. In lower angle, where there's lower energy, the goofy old man put that down wrong first. How would you have to dress? It's going to be colder, right? Because there's not going to be as much energy per area. In other words, that would be colder temps. It's like when we are, looking at the 24 hours of daylight in the Arctic. The sun's relatively close to the horizon. It's just kind of circling around. So another way, I guess, then of saying that is, if we've got that high angle, it's going to equal high energy. Sheesh. Sorry, guys. My pen got stuck on my little writing pad here. So this relationship is proportional. Up, up, down, down. This relationship was inversely proportional or opposite. Up, down, down, up. So what relationship between area and energy can you conclude from this activity? And I want you to think about warming something up. Imagine you had a bowl of soup. So, here's your big bowl of soup, and then you had a cup of soup, your tiny cup of soup. And you put both of these guys on the exact same stovetop, and you turn on the exact same amount of heat, and you leave them on for the exact same amount of time. Which soup is going to get hotter faster? The cup or the bowl? Obviously the cup is, right? So what relationship between area and energy can you conclude? Well, I would say a lower area, or if you want to say a smaller area, maybe that sounds better, right? I like the way that sounds better. Smaller area gets more energy per area. So, again, it's the same energy from the sun or the flashlight, but we're heating up that smaller area, little bowl of soup, cup of soup, versus a bowl of soup. So what would you expect to change on Earth as the sun angle is altered from low to high? Well, let's just kind of take a look at Cash's map here. There's Earth. There's the old equator at 0 degrees, like a little pokeball. If you are up here or you're down here, long johns, mittens, winter hats, flip-flops, swimsuits, beach towels. Why is it so much hotter throughout the tropics? Because your sun is beaten down with those direct rays. You've got the sun going back and forth overhead like this. Whereas, you've got the sun going back and forth overhead like this if you're near the equatorial regions, you're near the equator. Whereas in like Dearborn Heights or in Michigan here, we've got the sun kind of going like that. We're not always getting real high sun rays. Sometimes we got low, sometimes we got high. Hence our 4 distinct seasons of winter, summer, and spring and fall are kind of like our betweeners. So explain the relationship of seasons and sun angles. And I want you to do this on your own, but I want you to try to use these words. Sun angle, name the seasons, talk about what the tilt of the earth does, how much energy you would get with those different angles, how much area would the sun be cooking there, and keep in mind that this is going to change as we revolve around the sun. So I'd like to see what you can come up with this, because you're all little creative scientists. But, again, we've seen this before, right? If there's the sun and the old spaceship Earth revolves, orbits, makes its trip around the sun, and there's times when we're leaning towards the sun, we're actually farther from it, but we experience summer. And there's times that we're leaning away from the sun, and that's in reference to northern hemisphere. And even though we're closer to the sun, that would be our winter. And at our equinoxes, or our falls and springs, we kind of wind up with some betweeners. Some of you are probably able to rattle off where the sun would rise and set at each of these locations, briefly describe the sun angles we would get, and actually talk about the length of daylight hours. So if you find that you're struggling piecing together all this, reach out for some help. Hopefully that sheds a little more light. See what I did there? Shed a little bit of light. Insulation. Sorry. Till we meet again. Take care.